what we're going to look at today is we're going to look at what happens when we add HX. So HX could be HCl, HBr, HI to an alkene. We're going to look at basic mechanisms, looking at predicting products. Tomorrow in the do now, we will go backwards. We'll see if we can take products and go backwards to a reactant. But as we go through all of this, we have to keep Markovnikov's rule in mind. So Markovnikov's rule is that the hydrogen will add to the less substituted carbon, and the carbocation will form on the more substituted carbon, because the more substituted the carbon is, the more stable that carbocation is. So when we say that something adds Markovnikov, and we will use that term often, when we say that something adds Markovnikov, that means hydrogen goes to the less substituted side. The halogen will end up going to the more substituted side, because the halogen is going to go where the carbocation forms. And the carbocation forms on the more stable or the more substituted carbon. So to summarize, this was the last slide that was in your notes. If you actually flip back to page 8, this was the last slide from the video. So here again, when it says it follows Markovnikov's rule, you're forming the more stable carbocation. So the halogen will add to the more substituted carbon, the hydrogen will add to the less substituted carbon. This is called a regioselective reaction. So when I say think about regioselectivity, you just have to think about, does it add to the more or the less substituted carbon? We're always going to show the two-step mechanism. We are no longer going to say, here's our reactant, here's our product. More than likely, we're going to say, here's our reactant, here how the electrons move throughout this mechanism, and then here's the product. And so we'll show that attack. So see, it's nucleophilic attack. The alkene is the nucleophile attacking the hydrogen. We form a carbocation, and then the halogen, so Cl minus, Br minus, I minus, acts as the nucleophile to attack that electrophilic carbocation. You could have hydride or methyl shifts if a more stable carbocation can form. And we will look at a couple mechanisms where we could have a major product and a minor product based on if the carbocation can shift or not. So if we take a look at the first mechanism, so bottom of page 9, draw the mechanism and the product of the reaction. Now again, you're going to see this little disclaimer pretty much on every example. Some lone pairs might be shown, some might not be. You don't have to show them, but what you do need to show is formal charge. So the positive on the carbocation, the negative on the halogen. We always need to make sure to show that. So if we take a look at what this actually looks like step by step, almost always my mechanism is going to go this way, right? I'm going to take what happens, I'm going to have an arrow down, arrows down, and around. Units 4 and 5 for us are all reactions, so we're just going to keep looking at all these different mechanisms. So what happens in this, and sometimes you might see me write HBr like this, just to help you see the electrons. The more comfortable we get with it, the less likely it is that you'll actually see that bond, but it's just to help. The very first step is nucleophilic attack by the alkene. So the alkene here, right, the pi bond electrons, these excess electrons make this entire molecule act as a nucleophile. I'm not going to ask you to label, but if we're mentioning, right, nucleophile is what has those excess electrons. The electrons, be specific with your arrows. Where are the electrons coming from and where are they going to? So the electrons from this pi bond are going to attack the hydrogen. So notice how I'm trying to be specific with the arrows. They're coming from the pi bond, they're going to the hydrogen. So the electrons in the pi bond are going to attack the hydrogen. They're going to form a single bond. Now hydrogen can't have two bonds. So the single bond between the hydrogen and the bromine, those electrons will go to the bromine. It's going going to act as a lone pair. So we have the electrons attacking the hydrogen. That's going to form a single bond. Now, if I look at my first part of this mechanism, we always want to show all the intermediates. Right now in AP, we're talking about kinetics and we're talking about intermediates. Right? If you remember from AP, an intermediate is something that is created and then used up. A reaction mechanism is showing everything that happened. So we want to show what happens when this alkene attacks the hydrogen. So let's see if I can draw my hexagons, kind of. Oh, that's a pentagon. Yikes.
One of those two.
It's fine. Right? So we're going to have, these electrons are now gone. Right? They're not gone, they just have formed a single bond. But that single bond went to a hydrogen. I'm going to show where the hydrogen went. Markovnikov's rule says the hydrogen gets added to the less substituted carbon. So the two carbons that we are looking at are here and here, on either side of the alkene. This has 1, 2, 3 carbons connected to it. This has 1, 2 carbons connected to it, which means it also has a hydrogen. This is the less substituted side. That's where the hydrogen is going to go. So I'm going to show the hydrogen. Is there technically another hydrogen there already? Yes. I'm just showing the hydrogen that's coming from the HBr. Now what that leaves me with is fewer electrons than there should be here. All right, we've lost some electrons from this carbon, right? Originally, this carbon had 1, 2, 3, 4 bonds connected to it. Carbon should have 4 bonds to have a formal charge of 0. Now this carbon has 1, 2, 3 bonds. Here is where the carbocation is going to form. Now the other product that we have, we don't want to forget, is the bromine. Now has 8 valence electrons, and so it's going to have a -1 formal charge. So the hydrogen added to the less substituted side. Now if we take a look here, whenever we're trying to ask ourselves, will a rearrangement occur? You just want to see what type of carbocation did we form. It's already the most stable carbocation that we can form. There's no rearrangement. So this carbon has 1, 2, 3 carbons connected to it. That's a tertiary carbocation. That's already the most stable carbocation that we could form. Now, because our carbocation is stable, now we will actually see another nucleophilic attack, but now the nucleophile is Br-. So now our nucleophile is Br-, and what's going to happen here is some of the excess electrons from bromine are going to attack that positively charged carbon. Positive and negative will attract. So if we look at the mechanism, it doesn't matter which lone pair you choose to draw your arrow from. That does not matter. But what's important is that you show the arrow coming from a lone pair pointing to that carbocation carbon. And when we draw those lone pairs, that's going to form a single bond. So it's going to attack and it's going to form a single bond. Oh, here we go. Let's see if I can draw this again. All right, so another hexagon. Much bigger pentagon than before, but that's fine. Now, do you have to show the H that came over here? No, you don't. I showed the hydrogen initially just so that you could see the hydrogen added to the less substituted side that left that other carbon with too few bonds, so it had a +1 formal charge. So this is our product. However, when it says draw the mechanism, you have to make sure you show how the electrons move, where the electrons are going. You're showing the intermediates. You don't have to label the nucleophiles. right, so like if this was the nucleophile, this was the electrophile, and then it switched. What you have to show are how the electrons move. Questions on the first mechanism? So see if you could do, right, you can work with your groups on this one. See if you can do this mechanism. So talk to your groups. What's the attack going to look like? Where's the carbocation going to form? I'll give you a hint. There are no rearrangements here, or there shouldn't be rearrangements here. But work with your groups to see if you can draw this mechanism.
What do we do now?
Just show the whole mechanism.
Wait, what?
What's happening? So you have to show the hydrogen moving. Like here. All right. Oh no. Oh well. So make sure you're showing step by step. So here's the first step. Again, I showed the hydrogen. I showed the hydrogen because that's where it's going to add to the less substituted carbon. So when you're looking, here's your first carbon, here's your second carbon. The hydrogen will go to the less substituted side. That is the definition of Markovnikov's rule. This is already a tertiary carbocation. There's 3 carbons connected to it. It's tertiary already. So then, step 2, again, doesn't matter which lone pair you pick from. You need to show the lone pair attacking the carbocation. And then, this is what you're going to have. So, when it says, draw the mechanism means show the electrons and how they're moving. Show the intermediates. The carbocation and this halide are the intermediates. They're created and then they're going to be used up to create the product. Now we're going to look at, we have 2 more examples. We're going to look at what happens if we don't have the most stable carbocation already created. And so what we're going to do is we're going to have to start thinking about what type of carbocation do we have and how could we make it more stable. So here is the alkene, and now we have HCl. So start the same way that we started. The pi bond electrons are going to attack the hydrogen. So pi bond electrons are going to attack the hydrogen. If you don't actually redraw HCl, sometimes I'll just put a little single bond in between, just to show that those electrons are what go to chlorine. You have to make sure you're showing your arrows. And so then we show our intermediate. Hydrogen adds to the less substituted side. Hydrogen will add to this side. So I look at what happens. Hydrogen will add here. Do you have to put the hydrogen on the less substituted side? You don't have to, as long as you remember that that's where you added it to. But now this carbon has 1 too few of bonds, which means this is the carbocation. How many carbons are connected to this carbocation carbon? How many carbons are connected to it? 2, right? 1, 2. So this is a secondary carbocation. Now I need to make sure I show my other product, which is Cl-. Is a secondary carbocation the most stable carbocation that we could have? No. So a rearrangement could occur. Right? We could have a rearrangement. When you have the potential for a rearrangement, you actually have 2 possible products. We have the major product, and we have the minor product. I'm going to show both of them and how we get both of them. The minor product assumes that no rearrangement occurs. The reason that that's the minor product is because a secondary carbocation is not the most stable carbocation. So this is not going to be the most likely product to form, but it still could form. So if we look at the minor product, we just continue this mechanism like we had before. We assume no rearrangement. So lone pair from the Cl- is going to attack that secondary carbocation. And then we get this. This is the minor product. Minor product because a rearrangement is likely to occur. Now, if a rearrangement occurs, so now here's where this is going to kind of split off. Oh, I'm not going to use that color. All right, this is where it could split off. I'll label this and then change colors. Let's assume that a rearrangement occurs. When you're looking at a rearrangement, you have one of 2 rearranging. A hydride shift or a methyl shift. And it can only come from one of the carbons right next to the carbocation. So this, we have hydrogens that we could shift over. If we shifted one of the 3 hydrogens over and the positive came here, what type of carbocation would that create? Primary. Primary is even less stable, so we don't want to shift it to this side. If I shift it to this side, we don't have any hydrogens here. This carbon is connected to 1, 2, 3, 4 other carbons. But we do have a methyl group that we could shift over. Right, so one of these methyls could shift over. So if this methyl shifts over, what will happen is we will have a methyl here. Now this carbon only has 3 bonds. The carbocation has now shifted here. Now what type of carbocation is that? Tertiary. That's the most stable carbocation. Now we can finish up the mechanism. Now we finish up this mechanism. Lone pairs to the carbocation. The major product is this. So the major product is after a rearrangement occurred. So you can have a major product, you can have a minor product. The minor product is assuming no rearrangement. Major product is looking at the rearrangement, rearranging, and then continuing the mechanism. Questions on this? We have one more after this. All right, if there aren't any questions, I want to have you actually see if you can do this one with your groups. Right, use the example that we just did to help. If you can have a rearrangement, you need to show your major product. Oh, I just said to show the major product. Okay, so you don't have to show the minor product in this one, just the major product. If this didn't say major product, you would need to show major and minor both. So work with your groups, show the mechanism. How do the electrons move? What has to happen? If a rearrangement occurs, show that mechanism as well. And I'll work through it up on the board as well. We're going to start getting back into cycloalkanes, so practicing our hexagons. So what I'm actually going to show is I'm going to actually show the mechanism that occurs for the shift. This is a secondary carbocation, right? If I were to move it here, I could have a tertiary carbocation. If there's a way to make it tertiary, we want to do that. To make this into a tertiary carbocation, what's going to happen is we're going to have a hydride shift. So the hydrogen that is connected to this carbon, because right now it only looks like this has 3 bonds, but we know, because it doesn't have a formal charge, it does still have a hydrogen. So the hydride shift, the hydrogen moves over 1 carbon. So the single bonded hydrogen actually moves over just 1 carbon, which then leaves us with a tertiary carbocation. So leaves us with a tertiary carbocation. Now we can continue the mechanism. So we still have Cl minus, chlorine acting as a nucleophile will attack that carbocation, form a single bond. So the major product is this. Now if it asked for both, we could go from this secondary carbocation to show the minor product. But since it just asks for the major product, we only have to look at after the rearrangement. But you always need to ask yourself, can we rearrange the carbocation to make it more stable?